Energy conservation is a strict rule, but it has a massive blind spot. The physics of perfectly conserving energy allows almost any process to run in reverse, yet we only ever experience them running one way. The first law of thermodynamics tracks the total energy in a system. If a frictionless pendulum swings indefinitely, or if heat flows into a cold object instead of out of it, the first law's books balance perfectly either way. It cannot tell the difference between forwards and backwards. But drop a hot copper block next to a cold silver one, and you see a strict physical reality. The heat always flows outward, bleeding directly from the high-temperature block into the low-temperature one. It never spontaneously runs in reverse. Something else breaks that symmetry and decides the direction nature will allow. That something is a specific thermodynamic property called entropy. Quantifying entropy allows us to predict whether a physical process can occur, defining the one-way trajectory of the observable universe. Many introductory science courses rely on a common shorthand, that entropy represents messiness or disorder. But that visual metaphor is flawed. Judging a physical system based on visual messiness is a subjective human judgment. Disorder is a vague visual concept that fails to map onto the rigorous mathematics of thermodynamics. Engineers utilize entropy as a calculable state property, as measurable and objective as pressure or volume. Its true function is strictly mechanical. Entropy is a bookkeeping quantity used to track exactly how heat moves at a given temperature. Relying on hard numbers allows us to accurately predict how real-world energy systems actually behave. Rudolf Clausius defined entropy in the 1860s through his analysis of steam engines, treating it as a functional necessity of thermal physics. Clausius found that for an idealized, reversible process, the change in a system's entropy is the heat added, divided by the temperature at which it is added. That specific mathematical relationship gives it concrete, measurable units, joules per Kelvin. You can calculate this during any physical change, like heat spontaneously leaving a glass of warm water to melt a freezing ice cube. Because you are dividing by temperature, the math forces a strict outcome. The entropy lost by the warm water is a smaller number than the entropy gained by the cold ice, because dividing that same amount of heat by the lower temperature yields a larger result. This leads to the second law of thermodynamics. In any real, spontaneous process, the total combined entropy of an isolated system must increase. If you ran that equation backwards, trying to move heat from the cold ice to the hot water, the total entropy of the system would drop. The laws of physics forbid that, which is why heat only flows in one direction. Decades later, Ludwig Boltzmann gave entropy a deeper meaning by looking past the macroscopic equations and focusing on the statistical behavior of individual atoms. He made a strict distinction between a macrostate, the large-scale properties an engineer can easily measure, like overall pressure and temperature, and a microstate, which is one specific, exact arrangement of every single molecule's position and energy at a given instant. Boltzmann realized that a single measurable macrostate can be produced by billions of different, invisible microstates. This concept is called multiplicity. His insight, which is carved directly onto his gravestone, is that entropy is proportional to the logarithm of the number of these accessible microstates. The core statistical truth is simple probability. A system naturally drifts toward the microstate that has the most possible microstates, simply because there are overwhelmingly more of those arrangements available. You see this when a drop of dark dye is released into clear water, irreversibly unfurling and spreading through the glass. The dye molecules aren't being actively pushed apart. They spread out because, mathematically, there are vastly more ways for the molecules to be distributed across the entire volume of water than bunched tightly together in one spot. This replaces the subjective disorder metaphor with the precise concepts of multiplicity and energy dispersal. The macroscopic arrow of time we feel every day, that the past is more ordered than the future, is at its absolute foundation driven by this inescapable microscopic counting. Moving from abstract atoms back to heavy iron, this exact property governs the absolute limits of the industrial world. With a mechanical heat engine like this demonstrator, the goal is to convert heat from the hot side into physical work at the spinning flywheel. But the second law of thermodynamics imposes a harsh reality. No engine can ever turn 100% of its heat into useful work. Every single engine must reject a fraction of that heat out to a cold reservoir, or the mechanism simply will not run. This chart illustrates the Carnot limit. It defines the absolute maximum possible efficiency an engine can reach, determined entirely by the difference between the hot and cold temperatures it operates between. A mandatory chunk of energy must split off as waste heat. No mechanical design and no material can ever beat this limit. Crossing that red line would require decreasing the total entropy of the universe. Every real-world machine we build, from standard car engines to massive steam turbines and power plants, falls significantly below this theoretical ideal. Rejecting waste heat isn't a flaw in human engineering. It is a mandatory tax demanded by the universe to ensure that total entropy always increases. Engineers apply entropy as an active tool to dictate and validate real-world design choices. Before building a prototype, an engineer computes the exact entropy states of their working fluids directly from established reference tables. Calculating the total entropy change acts as a definitive pass-fail test. If a proposed design requires the total entropy to drop, the engineer knows mathematically that it is physically impossible to build. They still manually calculate the classical heat over temperature equation to map the strict boundaries of their thermal systems. When running physical test stands, sequential temperature readings provide a hard data trail, proving that total entropy is increasing across the process, exactly as predicted. Real-world operations introduce entropy generation. Every point of mechanical friction, every pressure drop in a pipe, and every unintended heat leak constantly generates new excess entropy. This connects directly to a system's efficiency. Every bit of unnecessary entropy generated in a machine exactly equals a measurable amount of useful work permanently destroyed. Entropy provides the exact quantification of energy dispersal, mapping the physical behavior of a system onto a rigorous scale. This single value decides the direction heat will flow, establishes the inescapable arrow of time, and sets the absolute ceiling for human technology. The entire discipline of thermal engineering is a continuous battle to minimize this entropy generation, scraping out fractions of a percent of efficiency from refrigerators, turbines, and engines. To build better systems, you have to look past the flawed analogies and start calculating the physical math. The next step is to review the real thermodynamic equations and study the step-by-step engineering breakdowns. You can master the reality of thermodynamics by visiting ProReadyEngineer.com.